Hey, this is Dr. Kofelt. Welcome to part 7. This is still chemical equilibrium, and in this part we're going to look at how changing the concentrations will change the equilibrium, and then we're going to look at, if it's a gas, how pressure and volume changes can change the equilibrium. These last two sections are based on LeChatlier's principle. And LeChatlier's principle is basically saying that if you disturb the equilibrium, that it's going to shift in order to retain or re-engage that equilibrium. So once it's at equilibrium, the concentrations of all the reactants and products should remain the same. But if you change the conditions, okay, that is the temperature or the concentration or whatever, then the reaction is going to then react some more to restore that equilibrium. Because remember, that equilibrium point is constant. And if you change the temperature, it has to find a new set. But if you change other things, it's going to find that same equilibrium status. So if the new concentrations are different, the equilibrium constant stays the same as long as it's at the same temperature. So LeChatlier formally says if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize the disturbance. Okay? So ways you can stress a system: change the concentration. If it's a gas, you can change the pressure volume. You can change the temperature, or you could introduce a catalyst. So the effect of concentration, if you add or remove reactant or product, the reaction is going to move to compensate for that. So if we remove something, the reaction will try to replace it. And if we add something, it will try to get rid of. So I think of this as the push me, pull me, okay? If you remove something, it's going to try to replace it. So if you're removing it, think of you pulling away while you're removing. If you're adding something, think of it as you're pushing that into the reaction. And let me show you what I mean here. So if you have this reaction, CaCO3, which is a solid, in equilibrium with CaO and carbon dioxide, all right? And so if I add CO2 to this, I'm adding, so I'm pushing. So if I add CO2, I'm pushing it to the left. If I add CaCO3, what would be the effect? Nothing. Why? Because solids don't affect equilibrium. Gotcha, didn't I? Okay, but if it's a gas or an aqueous, then changing something will absolutely, you either push it away or you pull it towards. Okay, now, and that's for concentration. Now, in part 8, when I get to the end, I'm going to go through a whole lot of these, and so you can kind of get the hang of it. All right, so the effect of adding a gas to another gas phase, if you add gas reactant, you're going to increase its partial pressure, and it causes it to shift to the right. It's the same exact thing as when we were doing those concentrations. But if you add an inert gas, that is a gas that does not react, it will have no effect. Okay, so it'll say if it's an gas or not, because you're not expected to have that level of knowledge at this point. Okay, so you've just got to remember a little about Boyle's and Dalton's law. If you increase pressure, the equilibrium will shift to remove the pressure. All right. And remember that pressure and volume are inversely proportional. So if you know what's the effect with the pressure or the volume, then the other one is just going to be the opposite effect, right? That was Boyle's law. In Dalton's law, if you increase the total pressure, the partial pressures of everything, all the gases will increase by that amount too. But the value of the equilibrium constant will be the same unless you change the temperature, all right? So when the volume decreases, When volume decreases, pressure increases. All right. So since there are more gases, so you are decreasing the pressure because you're increasing P, and so V is decreasing, and so you're squishing those gas molecules a lot closer together, and so you since they're closer together, there are more molecules on the reactant side. Okay, so what you're trying to do is you're trying to shift the equilibrium to the side with fewer gas molecules. So when you increase pressure, you're going to shift to the side with fewer gas molecules. If you decrease the volume, you do that, right? Because they're inversely proportional. So just remember one and remember that the other one is the opposite. Okay? So P increases, the shift is towards the fewest gas molecules. And guess what? If you decrease the pressure, it's going to shift to the side with the most gas molecules. Doesn't that totally make sense? Okay? So, you look and you see. Remember, we kind of did this with the delta N thing when we were doing calculations between Kc and Kp. You've got 2 moles of KClO3, which is a solid, and you have 2 moles of KCl, which is a solid, and 3 moles of gas. So you have 3 moles of gas on this side and 0 moles of gas on that side. What is the effect of decreasing volume in this first one? So I decrease the volume, which means I increase the pressure. So if I increase the pressure, then it's going to go towards the fewer gas molecules. So that means it's going to go to the left in this case. All right. If I increase the volume, then that means that I'm decreasing the pressure. And when I decrease the pressure, it goes to the side with the most gas molecules. So it's going to go to the right. If I add an inert gas, what will happen? Nothing, right? Because it's not going to react with an inert gas. All right, this is the hardest rule to remember, so just make sure you memorize this one. If you increase the pressure, it's going to go to the side with the fewest molecules, okay, the fewest gas molecules. And that's all we're doing in this part, and I'm going to continue LeChatlier in part 8, and then I'll do a review of all the conditions of LeChatlier at the end of that.